won't mind. Sarah and I are going to quickly summarize for you the work of Anaïs Pacquaut. She's our PhD student. She's going to defend her thesis in November, so I stole some of her slides. Her work is on the measurement of the HTC of the envelope during occupancy. Oh, wait. Yeah. So, some of the methods that you know about require buildings to be vacant during measurements, like the Sirene method, so that you can ignore the influences on the heat balance of the building, no ventilation, no electrical equipment, shades are closed, etc. But that is not always possible, so we also look for the methods that can be done during occupancy of houses, in our example, houses for now. Advantages of doing this during occupancy is that you can rely on longer periods of measurements, but you also need to only rely on non-inclusive monitoring equipment that does not occupy entire rooms like this. So we tried to summarize all the influences on the heat balance of the building that may influence the HTC estimation during occupancy, those things that are neglected in methods like Serene. So typically the presence of occupants due to their metabolic heat gain will bring some heat to the balance. The HVACs, especially the ventilation, flow rates, lighting, appliances, heat gain from indoor equipment, and the interaction of occupants with the envelope, windows, and blinds, which are variables which are not often measured. So all these factors come in addition to the heat balance of the building compared to methods like cube, Serene, etc. I'm just going pretty fast so that we can show some results. Since we rely on longer measurements, the method is not bound to one type of model. The question looks a bit wonky. The method is not constrained to one type of model, but since the measurements can be long, we can assume long sampling periods of several days, so not time series models. So we started with linear regression models, which are very simple and very efficient in our experience. The linear regression model, heating, and all the indoor heat gain equals HTC times temperature difference, indoor-outdoor temperature difference. Okay, but what's new in these methods in our work? What's new is that we are doing Bayesian inference in order to formulate the uncertainty of the input variables and to estimate the uncertainty of the output variables. In the Bayesian framework, everything is uncertain. Everything is a distribution of probability. The input parameters, the unknown parameters, the measured variables, and the output variables that are not calculated. So this typical equation for the ordinary linear regression comes with an array of prior distributions which represent the uncertainty on the indoor temperature measurement, on the solar heat gain from occupants, ventilation, etc. For instance, the heat gain from occupants, we assume that the number of occupants per day might be known or might be estimated, and then the amount of heat related to this is uncertain with a certain normal distribution around a certain average and a certain standard deviation. Okay. The indoor temperatures that is measured, and using this equation, it's not one value of indoor temperature. What we measure might not be exactly representative of an average indoor temperature that we can just put into this balance equation. So there are two variables. There are one observed indoor temperature and one unknown actual indoor temperature, and there's a difference between the two. It's called a latent variable in this Bayesian methods. Ventilation also. Ventilation flow rate is unknown. Well, it's not completely unknown. There's a prior distribution on it. We assume it's what is this? Not uniform distribution, it's not normal distribution. What did she do?
No, it's a deterministic.
Deterministic?
Yeah, it means that unlike the other parameters, normally in a Bayesian framework, you'd have an update of every distribution, but this one, it couldn't work. So the uncertainty around the ventilation parameter is kept untouched, yes, unupdated up until the end. So it's basically, it just propagates the uncertainty you have on ventilation. And since I'm interrupting you,
go ahead.
Let's just highlight the fact that we have a ventilation term here, which means that the HTC here is meant as a transmission coefficient plus infiltration
not including ventilation.
When satisfied with just a global HTC thing.
And appliances assume that we measure the consumption, the electrical consumption, and the amount of this consumption turned into indoor heating is not known, but it's weighted by a coefficient between 0 and 1, so represented by a beta distribution. So it's bound between 0 and 1. Okay, so first, Anaïs applied this method to simulated data, one house in 8 climates in France, to see if the HTC estimation was variable in the same house in 8 climates. Hopefully, we hope that it's not. And then in one climate, she varied the prior distributions to represent the fact that we may not know actually the actual ventilation flow rates. We may make a mistake when we estimate the metabolic heat gain, etc. And then what she did as well, on still the same simulated data, one climate, she tried to find out how long a measurement period we need to get HTC uncertainty that is acceptable. So these are the 8 climates. Good news, our purple method Bayesian is quite stable, is not influenced too much by the fact that we are in the southern region of France where it's warm, or the northern one. So usually in the south, we have high HTC value estimated because we overlook some of the solar gain. In our case, we make sure that we try to remove this variability. Influence of prior, this is still in purple, the various HTC estimations that you see if we pick different initial values of the ventilation flow rate here. So you see that it is quite variable, which highlights the importance of not just guessing the ventilation flow rates, but having an actual measurement of it or a good guess. Same thing for the other priors. Metabolic heat gain does not have too much of an importance on the HTC estimation. Solar heat gain coefficient has one, but here the variations are not too large. And the coefficient for the electrical appliance transformed into heating from 0.6 to 0.9. It has a little bit of influence on the HTC estimation. And then this is the influence of the period of duration of measurements. If you pick only 7 days of measurements during one whole winter, in the beginning or in the end, you see the variation of the HTC estimation is quite large. For 7 days is clearly not enough. And then things start getting better if you look at here 28 days, 35 or 42. So you need at least 1 good month of measurement in this method to get an HTC that is with a mean that is in the 10% range. Okay.
Now I have less than a minute.
We'll give you 2.
I might
you can have 2.
Oh, I can have 2. Great. So what Anaïs did then is, try her method on actual experimental data. So she studied 3 case studies. One is Miriam's house. So she got the data and, Anaïs could study it. This smart, I think we mentioned it at Saxium. It's a 3 winter, almost 4 winter data set with every kind of measurement you'd like to see. And one of the cases of the SMETA project. I'll just, give you a quick view on the smart. So we have 3 winters. So she picked 42 days in each winter to see if it made a difference. You'll see here in purple the result of her method. So they quite agree. There is one winter that is, well, it seems to be slightly harder than the others. The reference here is really, really large. But well, the method gives a result that's not that off. And then we see that the first winter, 2021, gives what? I think this might be something weird with occupancy, or maybe a set of temperature set point has been changed, or something with the system, because you see that it just goes up for no reason. We haven't explained it yet. The other two winters are quite alike in terms of data, and we see that both measurements are quite close in the end in orange and green. And last thing she did is, well, look at convergence of the methods. If you take the first 7 days and then you add days, at a certain point you'll see that if you span across winter, you'll have convergence of the measurements. And it's, well, what's interesting is that she found that from 30, 40 days, you have something quite steady. And so it's matched what she had found with a numerical study. Last slide. This was all published. She has already 2 published papers. One is soon to be submitted with the actual case study data analysis. And well, there are things perfectible so far. We don't have every single possible case study modeled in the method, but it looks promising. And it is a way under occupancy to rule out the ventilation component and have really the essence of the envelope performance. Yes.
Perfect. Thank you.
Thank you.